Yesterday we looked at this model of a transfer line, and again, the reason for the name, as I mentioned, is that it has more to do with a manufacturing context. Uh, it's a line in the same sense that the assembly line is, but is different in that an assembly line is kind of forced uh, movement, whereas the transfer line is a situation where there's queuing at each station. Again, there are contexts in which each of the different structures for modeling for manufacturing parts or fabricating parts is appropriate, but um, that's a different topic. What we're dealing with here is modeling it. Now, yesterday I talked about this sim event listener idea, and that's a very important one because it allows us to build models that are substantially that can scale up more and scale up more easily, and also be more readily verified. In other words, we can verify the components in a manner which is simpler than trying to verify a great big spaghetti of an event graph, which is all one thing. So so today I'm going to talk about this transfer line component, which is basically doing the same thing as the one that we talked about yesterday, except that it omits all of that stuff up in the beginning. In other words, if you the idea is it's only going to model the part of the system that processes the parts once they come in, and it doesn't model the arrival of the parts. And that's similar to what we did with the simple server component the other day. Okay, so the state variables are the same. I'm sorry, yeah. Okay, so the parameters are the same with one exception, and that is that we don't have the inter-arrival times. So the idea is that as a component, it's just going to model the service part of it. The arrivals are going to be handled elsewhere. And so the idea is that you build this component and it will do a certain job, but it relies on other components. In this case, it will rely on another component to produce that arrival event at the first workstation. Okay, so the state variables are the same. Again, we have n workstations. Again, just with the parameters, we have n workstations. The service times at each work center and the number of servers at each workstation are going to be slightly different. And in the second bullet, I called it a work center, and the third one I called it a workstation. They're both, I mean the same thing. I don't know why I gave them different words, but basically the workstation is where there are these identical machines or servers. Okay, again, the state variables are the same, and what's different here from some of the first models that we did is that the state variables themselves are also an array. So when we get around to modeling this, implementing this, the number in the queue is going to be an array rather than a scalar. And likewise, the number of available servers is going to be an array rather than a scalar. So, but we're not worried about the implementation yet. Here, the idea is that the component itself is all that we are looking at here. And as you can see, and if you contrast this with the event graph from yesterday, you'll see that yesterday there was the sort of arrival process like piece, and that there was this for loop that was initializing the, excuse me a second. All right. Okay, I'm back. Sorry for that. Can you hear me? Okay. Okay. All right. Now, if you will notice that this component looks a lot simpler than the one that tried to do um, the entire thing, and that was one of the reasons that makes it simpler is the fact that we're not trying to handle both the arrivals and the service piece of it. So you see, and in fact, what kind of helps with this is that you can see the two pieces. There are basically two elements to this event graph component. One is the initialization, and again, here it's a little more clear that the run event is responsible for initializing the state variables. In this case, because the state variables are arrays, we have to initialize them one at a time. And we do that using this, this event graph version of a for loop. And with each init value that passes I, then we set the appropriate value there. The main portion of the event graph is is again very similar to the multiple server queue one, with the exception that each event has an argument associated with it. And the key thing that connects these is this scheduling edge that goes from end service to the arrival. Now there are also some logically it's exactly the same as what was discussed yesterday, so I'm not going to go in detail through each of the events. However, there is one important thing that I need to emphasize here, and that is the fact that each event can only perform computations, if you will, based upon information that it has. And the information that each event has consists of only three things. There are only three places where an event can get information. One is from the parameters. The second is from state variables. So every event has access to every parameter and every state variable. And if you think of the analogy to the Java SimKit version of this, the parameters are modeled as private instance variables, and the parameters are modeled as protected instance variables. So what that means is that the events are modeled as methods, as instance methods. And if you remember, instance methods have access to all instance variables. So therefore, in the implementation, every event method has access to the parameters and the state variables. Likewise, every event in the event graph has access to parameters and state variables. So here's how that plays out. Let's just look at the arrival event in this case. Now, it has access to the array of numbers in the queue, Q0, Q1, Q2, etc. But the state transition is Q of I. And how does arrival know what I is? See, if this I were not passed in, then this state transition would be impossible. The only way that the event knows which index to increment the number in Q array is that it's been passed in. Sorry, my keeps jumping. Okay, so this is very important when you start implementing your event graphs that have parameters. Now, in the second assignment, which I did post and hopefully linked correctly, I've asked you to create 3 event graphs in that, and those event graphs do not require parameters. So so you don't have to worry about that for this one, but for the one after that, you probably will require parameters. And the thing to just as a check, if you have an event, then everything that that event does must be based upon things that that event knows about. So what does an event do? An event has a state transition and it has a scheduling edge. And as part of that scheduling edge, there are potentially 3 pieces. One is the Boolean condition. The second is the time delay, which in this here it's 0, but here it's a value. And the third is any argument which may any parameter which may be passed, which again is optional. But it is required if the scheduled event has as an argument, then the scheduling edge must have a parameter. Okay, that's an important syntax check, if you will. So if you have an event graph and you're scheduling an event, like in this case, say the start service event, and it has an argument, then every scheduling edge that schedules it must have a parameter that matches that argument. Now, it's not required that its scheduling edge must have a parameter as well. It either can or can't. In this case, they happen to, but that's not, this piece is not required. Okay, so lock that down again. If an event has an argument, then you must pass a parameter. And if it doesn't have an argument, then and you pass a parameter, then again, that's an error. Unlike Java, there's no compiler to give you a red squiggly of death, as it were. So you have to do that yourself. And just to kind of beat this dead horse, as it were, everything that it does, the state transition and everything on the scheduling, must be something that the event knows about. And again, there are only 3 things the event can know about: parameters, state variables, and any arguments that are passed in. So in this case, I is passed in. If I were not passed in, you wouldn't be able to do the state transition. Now look at the scheduling edge. It passes I as a parameter now to the start service event on its scheduling edge. Again, the only way it can do that is because it was told that I when it was scheduled. Likewise, the condition, let's look at this condition, SI bigger than 0. So the arrival event has access to the array of number in the system, number in the servers. It has access to the array, but it doesn't necessarily, that doesn't guarantee you know which of the elements of the array. Now, which ones? The ith element. So this I, again, is necessary in order to evaluate this Boolean condition. And over on the start service event, it's kind of small, but the TSI, that's the ith, the service time at the ith workstation. So again, as a parameter, you have access to the array of service time values, but you don't automatically have access to the ith one. You don't know which one it is in that array. But because start service has I as an argument, you know which one to pick off. And it may sound like I'm kind of beating this to death a little bit, but when it comes to formulating these, when you have to formulate yours, you really need to check to make sure that everything is based upon things that the event has. One common error that I see is that you might have an event that requires an argument, but no argument gets passed. Or you might have an event that has no argument and you're still passing an argument to it. Again, that's the moral equivalent or the syntactical equivalent of trying to invoke a method with a mismatch of parameters. Okay, so now the issue with this now, so here's a little dilemma though. The dilemma is that in order to get this thing started, we need an arrival event to be scheduled with argument 0. That's what kicks this whole thing off. Now, we have our arrival process, but that will not work. Why doesn't it work? Because the arrival process schedules an arrival event with no arguments. And this is looking for an arrival event with an argument. So the arrival process cannot work because it schedules arrival events with no argument. The transfer line component needs an arrival I event, that is an arrival event that has an argument I. So here's one way of doing that. It's kind of a creator arrival process. As you may know, I'm kind of terrible with names, but conceptually, here's what that component looks like. So here's our arrival process piece. So we kind of take the arrival process piece, but then we add to it that at every arrival event, it will schedule an arrival with an argument an argument of an integer, but it'll pass it the value 0. And so what this will do is this will schedule a sequence of arrivals with an argument, each of which has an argument of 0. Okay, so regardless of anything that we're going to use this for, this is something that well, it'll do what it does. If you were to just look at this event graph as it is, again, it has a run event, so this will that schedules an event, so this will actually run by itself. And what it will do is it will schedule arrival events and arrival events with an argument of 0. Okay, so how can that be used? Well, if we have an instance of that, which is kind of loosely represented by this box here, so that's one of these, and a transfer line component, which is one of these, and that listens for the creator arrival process, then whenever this arrival event with an argument of 0 occurs, then that will be heard and executed here. Okay, so that's how that's going to work. Yeah. Okay, so the next topic I just want to mention, and we'll be circling back to this at some point. And this is potentially confusing, so you just need to keep straight a little bit. And here, if you think back to when we were talking about sorted sets and how we can prioritize those, there's something similar that is sometimes helpful and sometimes necessary. So far in all the models that we have, it isn't really necessary yet, but occasionally it comes up. And that is, as you may have noticed, it is possible to have a sequence of events that doesn't advance time at all. In other words, you can have a sequence of events that are occurring with zero time in between. And by itself, the event list has no reason to schedule one or the other. Again, the event list criterion for ordering the events is at least the first cut, is based strictly upon what time it is scheduled. But sometimes you have an exact time tie with another event. And in that case, we can specify a priority on the scheduling edge. Here, P for priority. And again, this is the last option for the scheduling edges. And what that says is that when the event B occurs, again, remember the first criterion is scheduling time. So regardless of priority, the events that are scheduled before other events always happen first. But in the case where there's an exact time tie with another event, the one with a higher priority is executed first, regardless of what order they were in. So for our multiple server queue, to kind of be a little bulletproof on that, the idea is that the start service event needs to have a higher priority than other events. Now, normally this isn't an issue. For example, when the arrival event occurs, it will schedule a start service event with zero delay, providing the criterion, providing there's an available server. And because the arrival event is scheduled first, will occur first, and then schedule the start service next, then there's no need to worry about that. And likewise, the end service event, when it occurs, if there's somebody in the queue, then it will schedule the start service, but there's no issue in terms of that, because the end service will always happen first, just because of the way it's scheduled. But here's the thing: supposing just by chance that an end service and an arrival happen simultaneously. Now here's the thing: is that normally we use continuous random variables for this, and again, when in the random variable review, when I get around to that, there's a property of continuous random variables in that the probability that two of them are exactly equal is always 0. So the likelihood of this is very, very small as long as you're using continuous random variables. But sometimes you might use discrete random variables for the arrivals and the service times, and in that case, you may get time ties. So in that case, the priority is going to, in this case, we want to schedule start service with a high priority so that it occurs before any other scheduled end service or arrival events. Now that doesn't mean that the start service will happen before the end service that schedules it happens, because when the end service, before the start service gets scheduled, say, and if the next event were end service, then end service would occur first, and then it was scheduled start service. So even though they occurred at the same time, because the scheduling was sequential, the start service would still happen after the end service. So the priority doesn't change that. The priority doesn't change the order of the scheduling of events. What it does is it may change the order in which the events are processed by the event list, but only in the case of an exact time tie. Okay, just a couple of extra little snippets. and we modeled a for loop. We can model an if statement.
Sorry,
Pardon me.
excuse me.
Question.
Yeah, I've got a question to the slide before.
Okay.
Yeah. Is it important, is the order important, the condition or the priority, which has to come first?
Could you clarify the question?
Yeah, it's difficult for me because of the language. So in a
Yeah.
transition from one event to another, where there is a condition and a priority, and is the order of those both important when I start coding this transition?
Oh, yeah, yeah. I'll tell you now, but I can show you an example. Actually, I can maybe modify the example I was going to show you today for that. Okay, when you're, great question though. All right, so let's look at this arrival event, and we're now implementing it. When we're implementing it, this would be a method called doArrival. And so the standard order in an event is first you perform the state transition and then any scheduling. So first we do the state transition, and then the scheduling, the priority is going to be an optional argument in the wait delay statement. In other words, the order of execution is the way we implement the Boolean condition is with an if statement. In other words, we would say if s is bigger than 0, then we would do the wait delay. And the priority, if we have a priority, it would be put in the wait delay there. So in this case, the order would be state transition, evaluate the Boolean condition, and then the wait delay would include the priority if we had one. Okay, does that answer the question?
Yes, sir. Thank you.
Okay, and we'll come back to that when we look more at implementation. But again, very good question. Okay, so these Boolean conditions on the scheduling edges allow us to do something like this: is that if we wanted to model an if, like if B then C, I'm sorry, if B else C. So here, as an event, when A occurs, what we want to do is we want to either schedule B or we want to schedule C, but not both, but always one or the other. So that's basically an if-else. And so let's say the true condition would be based on I. So if I were true, we would schedule B. And if I were false, so this is not I, so if the Boolean condition is false, then we would schedule C. So this is how we would do an if. And again, you wouldn't see it just sort of in its naked form like this, but embedded within a larger context. This is how you would perform that particular task. And then, if you remember in programming, we can kind of chain, so let's say if B, else if a second condition, then C. So here's a situation where we have this: if the original Boolean condition is true, we want to do what's happening in B. And then in the code, we could actually say else if another condition, then C, and then if none of those are true, then we do nothing. Okay, so here's how you would do that in event, just pure event graphs. And you can actually you could actually combine these. But here I'm introducing, just for clarity, an extra event D here. All right, so let's look at this. If I is true, then B. Okay, fine. Else, if the second condition is true, then C. So now we have to, we can do one of two things. We can either combine the Booleans, or we can say, okay, if not I, then we'll schedule D, and then D will schedule C only if the second Boolean condition is true. So that's a way of doing a more complex if-else. And I think, okay, so now if let's say I wanted to do one or more of these, then we can just kind of expand that. So here I have 3 Boolean conditions, which may or may not be mutually exclusive. So if I is true, then we'll schedule B. If 2 is true, then we'll schedule C. And if 3 is true, we'll schedule D. And what is the relationship between these 3 Boolean conditions? Again, they can be anything that you require. Okay, so that's what I had there. Now, what I wanted to do is let me see if I have this here. I wanted to, right, let me show you this, an example of this listener thing. And this is something somebody's cleared stuff out here. Okay. If you remember last time, and this code is pushed to my my class code project. So if you pull that, then you can see what this is. If you remember last time, one of the things I did was this for loop. So here's how we kind of do a little for loop. And then I also did I show this? I think I did. Okay.
So we talked about it, the concepts, but I don't think you actually showed us the code.
Okay. So maybe I guess I better show you then. All right. So here's the for loop. Okay. So it extends SymEntity base, and we have a single parameter, which is the maximum. I'll call it max number. Again, that's how many times you want to execute the loop. Clear this. Okay, so we don't have any state variables, but we just have one parameter. And this is implementing that just the pure for loop that we had. Okay, so again, there's a 0 argument constructor that we will talk about toward the end of the course, hopefully. But the usual one is going to have all of its parameters and set them. So you make sure the parameters are set. Notice that you do not initialize your state variables. Well, in this case, we don't have any state variables, so there's nothing to initialize. All right, so here's the run event. Remember, that schedules init with an argument of 0. And then here's the init event, and here's how we implement an event with an argument on it. So the init event turns into the doInit method, and it had an argument I, which was an integer, and so we model that in this case as an argument that's an int. Now the condition, if you remember, was if I was less than the max number minus 1, then we schedule the next event, init event, in this case with 0 time, and with a value of I plus 1, passing I plus 1. Okay, so that's how we would do that little for loop thing. And when we run that, well, so how do we run that? Well, we initialize it, we instantiate it, and then the print line just verifies the parameter. So we see that this print line produced this right here. And that's to verify that the parameter that we thought we were passing, in this case 5, in fact was received. That's always something to check, because it's all too easy to just kind of accidentally drop one of them. Now, in this case, because this is going to run for exactly 5 init events and then stop, we don't need to stop the simulation explicitly. So again, initializing the simulation is what the reset method of schedule does. The start simulation, which occurs after that, is what actually runs it. So again, we run it, and here's what that looks like. So when we start, again, we always start with the run event on the event list. Then we move the earliest event to the current event. So in this case, it's always going to start with run. And run scheduled the init event passing an argument 0. And then so we hear here that after run happens, we see the init event on the event list, and we see that it's listed with its argument. So if an event has an argument, it gets listed. Notice that with the run event, it didn't have an argument, so nothing was listed. And any arguments get printed here. So the init event, that occurs. And then what does it do? It says first, if I is less than the max number minus 1. Max number was 5. 0 is less than 5 minus 1 or 4. So it schedules init 1. Then init 1 occurs. And then notice that these are the counts. So this is the first time that the init event occurs. This is the second time, etc. So now, again, 1 is less than 4, so it schedules the next one passing 1 plus 1. Then 2 happens, it schedules 3. 3 happens, and it schedules 4, and then 4 happens, and when 4 gets executed, we have 4 is less than 5 minus 1, or 4 is the condition. That's false, and so now the event list is empty, and so so everything ends. Okay, so that's the implementation of the for loop. Now, now here, in fact, I'm gonna modify this a little bit to show you because there was a question about the priorities. Okay, so so in this case, I want to initialize some events on the event list. If you remember, there was one use of this was to say, okay, supposing we wanted a certain number of events on the event list at the beginning, and that's what this is. So what this is going to do is this is going to the event we're going to create on the event list is just an event, and so what init is going to do. See, now what we're doing is we're extending the for loop. So now that has to be done a little bit carefully, as it turns out. So we're going to add an extra parameter. In this case, we're going to call it delay. And actually, I put this delay in here because I didn't want to talk about priorities just yet, but I'll show you how that can be adjusted. So now when we are subclassing a SimKit component like this, then our master constructor needs to have all of the arguments, all the parameters in the superclass as well as any that are added. So in this case, the for loop that we were extending had a max number argument parameter. And so we're going to kind of super that, but then we're going to add this extra one, delay. And what the delay is, that's going to be the time in the future that we schedule our additional events. So now our init event is going to do something a little different. It's going to to not only schedule the next init event based upon the maximum number, it's also going to schedule our new event here. And actually, I see I put this. I actually did put the priorities in. So here's how you put the priority in. So in the wait delay statement, if you leave the priority out, by default, it's just going to have a normal priority. But here I chose to to give it a low priority, and that's because I want all of the inits to happen before this one. Now the event itself isn't going to do anything. All we're trying to do is just show how to put these events on the event list at the very beginning. Okay, setter and getter. Just one point on the setters, and I'll kind of talk about this a little bit more this afternoon. When we're setting a value that has to be non-negative or positive, in this case, the delay has to be 0 or above. And if we happen to give it a value which is negative, we're gonna complain. But okay, so here we're going to instantiate it, and okay, we're going to run verbose. Now in this particular case, what I wanted to do is I wanted to stop them after all of the init events. So this is how I did this. Again, just press the I believe for this particular thing for right now. But when you run this, let's run this and see what happens. Okay, so I wanted a delay. Actually, here, tell you what. Just to show what how the priorities happen, if we give it a delay of 0 and we run it, then we will see this, still see the priorities. Okay, so again, verify that our parameters have been passed in. Always start with the run. Okay, so run schedules the init event. Now notice that here, the subclass did not define a run event. That was in the superclass, but it's there. So run event, that schedules the first init, passing at 0. That's exactly what the for loop was doing. Okay, so now here init 0 is occurring. And so it schedules init 1, and then also schedules this an event here as well. That is because of what this did. So when we want to execute what is in the, if we're overriding an event and we want to execute whatever was in the superclasses, we call the super. This is, but then if we want to do something more, then we just do it here, and this will happen after everything in the superclass. So we see that when the init 0 event occurs, it schedules the next init event with a parameter of 1, and it schedules this an event. Okay, now and then now control passes back to the event list. Now, when init 1 occurs, it will schedule init 2 and also another an event. But because it had this low priority, notice that even though they're all occurring at time 0, and one of these an event was scheduled before the init event, it happens after. Why? Because it was given a low priority. So we see that as the inits keep occurring, the an events keep building up. And so by the time we're finished with our 5th init event, then we see that there are 1, 2, 3, 4, 5 of these events on the event list. And then now at this point, the processing would continue. And so the next thing that would happen is that this instance of the an event would get executed and whatever it would do. But for our purposes here, all it's done is is just show how to put these events on the event list. Now, okay, so that's what I have time for today. And now we'll meet again at 1 this afternoon. And what I'm going to ask you to do there is to implement that simple server component version, in which you will reuse the arrival process that you wrote last week and use that to drive